Hi there, I'm Greg Watson, and welcome to this presentation in ASQ's 2021 Quality 4.0 Summit. This is being prepared by myself and Dr. Pedro Saraiva, who is a dean at the Nova University of Lisbon's School of Information Management. We're going to talk today about Shewhart's theory of maximum control as applied to Quality 4.0. And we want to actually think about this journey that statistical process control has gone from since the 1920s, when Shewhart first conceived it, to more modern applications in terms of what is called Kálmán filtering. So let's begin by thinking about what is the real issue that's being addressed when we talk about control. So Shewhart began his book with a quotation from Arthur Eddington in The Nature of the Physical World. And he said, when numbers are large, chance is the best warrant for certainty. In other words, it's the best way to assure that you get a degree of certainty because everything is devolving into probability. Another quote that was there came from a gentleman named Percy Bridgman in his book, The Logic of Modern Physics. And he described this situation that Eddington had talked about as a situation like this merely means that those details which determine the future in terms of the past may be so deep in the structure that at present we have no immediate experimental knowledge, that means measurement knowledge, of them, and for the present may be compelled to give a treatment from a statistical point of view based on considerations of probability. And this description that came from his understanding of physics, he was a Nobel laureate, by the way, was one of the things that Shewhart recognized was exactly what was happening in his approach. And Shewhart, in his Economic Control of Quality of Manufactured Product in 1931, said, the problem then is, how much may the quality of a product vary and yet be controlled? In other words, how much variation should we leave to chance? Today, the mathematical physicist seems more and more inclined to the opinion that each of the so-called laws of nature is essentially statistical, and that all of our equations and theories can do is to provide us with a series of orbits, if you will, of varying probabilities. So what Shewhart was doing when he talked about this in his quality contribution was he was bringing us into this idea of data as a foundation for building value and understanding of what's happening in processes. That they give us better control over the way we work and the way we deliver quality in goods and services. Now, modern quality thinking evolved out of Shewhart's discovery of these statistical process control charts in the 1920s. And he developed a methodology to extend scientific thinking to encompass hypothesis testing, data collection, experimentation, and summarizing results that can be applied to the practicalities for the production systems in order to be able to gain economic efficiency. Now, Shewhart's theory of control spanned 6 levels of thinking. And they began with, in his theory, he said he talked about belief that the future cannot be predicted. It's just basically, we have no belief of whatsoever, we're victims. And as he built up, he got to level 4, control within limits. And then level 5 was maximum control. And then level 6, laws of nature, exact science. And what we're going to focus on is these two, levels 4 and level 5. Level 4 is statistical process control. This is where most of us think of Shewhart's work. But he described a state beyond that called maximum control. So we need to understand what he had to say about that, and then how have we brought that idea forward since that time. And we can equate this idea to what we call today engineering process control, or engineering process monitoring. And so Shewhart's theory of control was in his 1931 book. He called this tool that he developed a control chart. And it's a graphical method based on statistical hypothesis testing. So every time we get a new data point, we put it on a chart and we evaluate how does it actually perform relative to patterns that we can deduce from the past relative to variation of the production process. And the method of application of this is called statistical process control. So we can evaluate patterns of behavior in the stream of data of that production process. Whatever it is we're measuring, whether we're measuring quality characteristics of the product itself, or we're measuring emphasis is placed on the process by which we are advancing that product through the manufacturing process. So Shewhart's control charts have 2 applications. One is retrospective analysis, and we mean by this that he's determining the current state of process based on a false alarm rate or a process capability. How good are we relative to what we did in the past? Second application is what we're really interested in now, is called process monitoring. And this is determining the ability of a process to maintain its state of control in future operations without creating this false alarm condition. And he was talking about this in terms of average run length. How long can we go under normal conditions before we get a false alarm detection? In a normal distribution with an X bar R chart, that's one observation out of 370 samples. So how does statistical process control work? Well, at the time that Shewhart created this method, all of the quality was done by inspection. Everything was done hand gauges by people doing these things, and they had very high error rates. They were used to evaluate performance within fixed specification limits. And if the key quality characteristic was outside of those limits, then it was either reworked or scrapped if it was unrepairable. So all inspection was done according to a 100% sampling rate. And then it was re-inspected after rework. Now, if we take a look at the Hawthorne plant, where Shewhart was serving as a support person in the statistical group at Bell Labs, they had 61,000 employees at that time, and 1/3 of those people were inspectors. So it's totally uneconomic to do this. Now, Shewhart shifted from this 100% sampling to using fixed sample sizes of 5 or 10 units and calculating average measures and plotting them on a chart. So these would begin actually to accumulate a chart after he's had a sampling rate and obtained about 20 samples. And then he would calculate the mean of those, each of those 5 samples or 20 times. And according to the central limit theorem, that would then be normally distributed. And this was the fundamental basis for his chart. Now, one drawback of that is it takes time to do that before you actually understand, are you making good products? So this is something that should be done in pre-manufacturing or product development to test out the line. Now, as we take a look at this, we study the past to manage the future. So here we have a control chart, and we see those red dots there. This is Minitab, and that's basically saying those are above the upper level control limit. So they are out of control conditions, what Shewhart called assignable clause and Deming later called special cause variation. And Shewhart said the reason for studying is to control quality of future manufactured products. So as we look at this control chart, what we see is at the last observation, this is actually kind of like a Bayesian moment in statistics. We have all of the prior information as being, if you will, what has happened in the past. And we can understand the probability of occurrence within those particular measurement boundary conditions. But what will be the future probability given that distribution? So can we create a future set of control or state of control in this process? So basically, this is how the continuous hypothesis testing works. We can use one of the Western Electric runs tests here, which is here, this is excessive variation, or we can use test 2 also for mean shift, or the other shifts for patterns within the variation. Now, statistical process control has some weaknesses. First of all, Shewhart's charts are useful for detecting large changes, or relatively large changes, around the order of 1.5 standard deviations. To improve this lack of sensitivity to control charts, and where smaller shifts were occurring in the process, the Western Electric runs test, the cumulative sum chart, the Q-sum, exponentially weighted moving average, EWMA, those methods were all developed in the mid-1950s to the end of the 1950s period. And however, all of those methods were still suffering from this problem of using data that had been sampled, so this averaging effect would minimize observations at the extreme extent of the sampled data set. So we're getting a sample that is an average, but we're not seeing any really high individual low or high observations because we're just getting the average data. That's all that's being recorded. So using sample data from either X-bar R or X-bar S charts, which Shewhart's created, can permit bad products to get to customers because we're not actually looking at all of those products. So as we see this, the next thing we see is that we need to increase sensitivity in these unitary samples. So one way to do that was we'd say, okay, if we measure every unit and catalog variation performance and look at all of this data as a time series. So now we're looking at what we call an individuals chart. And the individuals chart for a unitary variable, that means one variable that we're measuring, is basically something that was observed by Shewhart as a possibility and dismissed. In the 1940s it came out, but it really wasn't that operational. And it was only until the 1990s that this chart became popular, because we could actually generate observations of real-time data, put those in a data history, and then take a look at what's actually happening. But this was a very useful step forward towards contributing to an understanding of this state of maximum control. So what did Shewhart mean by maximum control? Well, he defined maximum control as the condition that's reached when the chance fluctuations in a particular observed phenomena are produced by a constant stream of a large number of chances. In other words, there's no random cause that's driving the dominant effect that creates some sort of pattern of variation. And Shewhart noted that approximate normality in the distribution can be taken as an indicator that you've reached maximum control. But this actually is got another assumption. And the assumption here is that that one variable is actually not only the dominant, but the only factor that is determining the quality of that total product. And that measurement system is sufficient to indicate variation in the level of interest. The sampling rate is adequate in frequency to determine are there any intermittent shifts in the distribution. It's also important that data is not average, which eliminates this excessive variation in individual measurements from being obscene. So digitized data capture, which happened basically possibility for it in 1987 with the advent of the Ethernet and distributed networks. By the early 1990s, we were bringing those together in manufacturing control systems and so forth. And so we could actually start doing things in real-time data analysis. And that changed the game. So we see there are some historical barriers to maximum control. This is what Shewhart had to say in 1931. He said, he concluded about maximum control, it appears that there is no characteristic of an overall distribution which in itself, in other words, is a single factor, indicates a state of maximum control. In other words, it's a useful concept, but we can't do it because there is no univariate control chart that actually works this way. He continues, we have also seen that normality of a distribution is not a necessary condition for maximum control. If I'm taking a look at things like time series data, it's not normal. So if I'm taking a look at unitary data of time series, we should not expect it to follow a normal distribution. It will have a long tail. And in 1931, Shewhart concluded about maximum control that it is of little utility. Now, while Shewhart's charts were univariate control, there was a desire happening to consider how will multiple factors work together, particularly in the chemical industry. And if you take a look at chemical industries, you'll see that temperature and pressure are always varying, so are flow rates. There's three variables right there that will actually determine the quality output of a particular chemical process. So how these work together to create a more controlled environment or understanding of that in these more complex situations became more of an important situation and a consideration with this advent of digital technologies. So this then says we need to move beyond univariate control, single factor, to bivariate control as a first step. So bivariate control says we're going to take two factors, measure them both, and then see what is the joint probability of them creating this control condition. However, just because all data is within the control limits as shown on either chart, it doesn't mean that jointly that creates a condition where the patterns are actually all in control of the total variation produced. So bivariate control charts is actually responding to this need for observations where data is having two factors that drive that control, or two factors dominate in the control of the quality of the output. So there can be also higher multivariate problems, 3, 4, 5, 6, 7. But the first step is going to be the bivariate. So how should we manage these cases to deal with control? Well, let's just summarize what we know about basic SPC. So while SPC is a powerful way to virtually and visually communicate the voice of a single process, it does have its limits. It provided a breakthrough mechanism in the 1920s, 1930s, and 1940s to allow us to visualize historical data. And this gave us improved understanding of process behaviors over just pure physical inspection processes. It also distinguished between two types of variation. Normal variation, which occurs just from natural fluctuations. That was what was called unassignable variation by Shewhart, which Deming called common cause variation. In other words, it's the variation designed into a process. And then also some that came out of particular influences in the process that could be assigned or recognized by the system. And these Deming called special cause variation. And these distinctions allowed us to classify the system under objective clauses that are potentially creating process disruptions or out of control conditions. So Shewhart also, though, identified this fifth level, maximum control. This is what we're calling engineering process control. This is also the domain that advanced control methods used in Quality 4.0 operate within. So let's turn and start thinking about what do we know about these bivariate control mechanisms. So what can be done to analyze in that multivariable domain, which we're finding ourselves in now? Well, we turn to the quality contribution of Harold Hotelling. So during the Second World War, Hotelling was part of the Stanford University Statistics Department, along with Professor Harold Walking and Eugene Grant. And they developed this 8-day statistics course that was given about statistical process control through over 3,000 factories in America. And this was also the course that was then taken to Japan in the post-war and was taught then by Jews in their post-war education programs for quality. But Hotelling developed a bivariate approach that he had actually created for designing the targeting systems for bomb sites on Allied bombers. And following this war distribution, he developed a bivariate control mechanism based on what he called the T2 distribution. And then he later created a more complex one, principal components analysis, as a multivariate, in other words, more factors, control mechanism. We're not going to consider that because that's only in probability space, and that goes well beyond what we're talking about in terms of this complexity, but it is something we need to think about along with the Kálmán filter algorithms in the future. So what the Hotelling T2 chart was actually doing was it was a method to monitor two quality characteristics that collectively determine an outcome. So they're more sensitive to process changes than the SPC charts. They're more robust to the normality distribution, and they're faster in detecting out-of-control conditions than those univariate charts. But their design, development, and interpretation is complex. And it's something that most people in operations will have problems with. And that's because when we start taking a look at this, we start saying that we are taking a look at understanding things in a very different way than is natural for people to do in the real world. So Hotelling created this concept when he observed that accuracy of bombing, for instance, is done by looking at the target, seeing where bombs actually hit, and calculating what's called center error probable, or CEP. And basically that was distributed normally, and would say how close we were to actually hitting that particular target. At the beginning of the war, that was close to a half a mile. Not very good. And so they wanted to get it down like to 100 feet or something like this per bomb. Now, what we're doing is we're actually dropping a whole bunch of bombs. So what they need to do is just to get it down to a reasonable amount where the majority of those bombs are on target. Okay, so bombs on target is exactly what the Air Force has as its objective. And so when we take a look at, the bomber is moving forward through space, and then the wind is coming at a cross angle. So we start seeing there's more complexity. There are multiple angles, there are multiple directions. And what we have to do is jointly measure those dominant forces of the aircraft heading and speed, and the wind direction and the drift that it's creating in that aircraft's movement. And then once we understand that, we can gain a better state of control. So high altitude bombing in World War II was done at 20,000 feet. And we see there was uncertainty in wind direction and speed. So this bias created an ellipse of inaccuracy. Because as I'm moving forward, I'm not getting much sideways drift, but I'm getting a lot of drift along the angle of flight. So that's an ellipse, it's not a circle. And then we start seeing this uncertainty is increased by the random effect of winds. You're at 20,000 feet, that's over 4 miles high, or close to 4 miles high. And so you've got crosswinds coming at lots of areas. Winds may change with altitude. And so we have this random wind effect happening. And so those are two interrelated variables. And the charts here show from the ordnance manuals of the 1940s, basically show the complexity of the geometry in the situation. And we're going to add speed and wind into this as well. So how do we actually manage that situation according to hoteling? Well, what the T2 chart does is it takes the two factors. So here we have two control charts, and it doesn't matter what they are. This is a chemical example. So we have pH and viscosity. And we measure them both, and both of those are in a state of control. But when we put them into the hoteling chart, what we start seeing is, whoa, there's one greatly out of control system. But we got no hint from that at all from the unitary control charts. Now, I want you to notice something, that the measurement scales on pH and viscosity are different. And here the measurement scale goes from 0 to 2.0. And this is called generalized variance. This is the T2 distribution. And so what he did was he created a new statistical distribution, which is the student's T distribution squared. Now, I'm not going to go into what that meaningful is, but basically as we start taking a look at that, we're looking at a covariance matrix. And so we see the individual effects here basically showed no unusual variation, but when we combine them, we see there is an out of control condition. So we get a much higher sensitivity by looking at the joint effect of those two variables that are driving this particular performance. Now, there are some weaknesses in this hoteling T2 chart. So it's no longer plotted in the magnitude of the direct measurements. That's what people are used to seeing. So we have to change the mental scope. So it's plotting a value that probably won't make sense to people. And since these are not familiar, this hoteling T2 chart really is difficult to compare because of this modified distribution it's using. But it doesn't really account for any correlation also that happens between the data. And so things like interaction effects, we're hoping that these two factors actually have no interaction. So pH and viscosity, should they interact? Probably not. So if we have, though, some correlation between them, we've got another problem. And so what is used here is called eigenvalues and eigenvectors. So we've created a matrix, basically, to increase the efficiency in data processing for large data sets. And what we do is then we do the math in this eigenvector dimension. It's a probability dimension. So the scale is no longer one that makes sense to people. And this is what is creating this difficulty to interpret the hoteling T2 chart. And it's also difficult to diagnose where are the problems coming from. Now, as you'll note in the footnote here, I have a tutorial. So those of you who want to understand more about this, please take a look at this tutorial. It gives you a basic idea of eigenvalues, eigenvectors, and how they operate. Now, if we take a look at this hoteling T2, we see that even though it's better than the two distribution chart, there are some concerns. One is they're only effective when this two variable problem, when those interaction effects are clearly understood, but we still have the diagnostics as being complex. And to cope with dimensionality reduction, there are other approaches that need to be done, like principal components analysis. But that analysis is done in probability space. We have to understand the eigenvalues, eigenvector stuff, and start understanding matrix algebra, partial least squares. So those were developed by statisticians, and they're using this more complex math. So we have to figure out how do we actually make those practical. Well, getting them for operators is too difficult, but we can do that in computer systems. And so that if we take a look at this in chemical problems, it's not at all uncommon to see up to 7 factors determining the probability of a good compounding or a good creation of a final chemical product. And so in this case, we have to move to something called applied optimal estimation. And this is where we introduce the idea of Kálmán filtering, which came from Rudolf Emil Kálmán. Now notice, he created this in 1960. And so we saw in the late 50s, early 60s, people are not satisfied with univariate control charts. They started doing things. The problem they had was the computers of its age, they're all manual, handheld nomograms and stuff like this, slide rules. And so they were not efficient for dealing with these things. And what Kálmán was doing was he was using a multivariate maximum likelihood estimator, kind of like what's embedded into regression analysis. He was stimulated by Ronald Almar Fisher's 1925 book, Scientific Research. from which he created DOE. And he says, what we're going to do is we're going to process signal-to-noise ratios, and we're going to try to look at less noisy outputs. So his work is advancing Shewhart's theory by operation defining this concept of maximum control and providing an estimator that would give us a multivariable dynamic case for operations in a real-time data flow. Now that's exactly the kind of thing we need to think about today, because if we put digitized sensors out in a quality 4.0 system, we're having lots of things accumulated in an organization, maybe with wireless links from those sensors to a computer system or a data historian. We're blending them together, and we want to ask the question, how well are we doing? So this opened the possibility to apply these real-time data systems for feedback and error correction. However, it wasn't until we got digital sensors that measured well, and also we got these systems that could correspond and communicate and bring the data together and then process that data, that we could actually make this very practical. So this multivariate Kálmán filter, it's looking for what is the coherent signal among all of these things in a stream of noisy or even incomplete data. So it's operating on the principle that noisy data comes in, less noisy data goes out, and ultimately our filtering process will lock on to the correct solutions. And it's going to also give us an estimate of hidden variables that we can't even measure directly, or that we have only inaccurate or vague understandings about. So the Kálmán filter is basically performing a Bayesian estimate using probability theory to discover the most likely coherent signals among all the various ones that mask the true value. So this is accomplished by taking input data over time, building on the prior probability of events that are filtered by new events, new measurements, with their adjacent noise and biases, and then creating an improved posterior result based on the old probability and the new observations. So this series of observations and calculations can be called a state space model. And we use this to monitor flow of data and improve estimation of the state of our particular production process. And this algorithm then is applied for controlling our system's performance. So the relevance of this to quality 4.0 is that it's providing a new way of thinking about digitization and data so that we can practice quality in industry. So this is particularly important application for quality 4.0. This and another application in terms of artificial intelligence and machine learning, which we're not going to talk about today, are basically two of the major tools that we can use, one that's data intensive and the other is information intensive, if you will, in learning about how we can make the future better. So current standard quality techniques do not manage this multivariate problem. And so the Kálmán filtering is something that it can allow us to improve the processing of big data to get better process control. And what happens is we have data streams coming out. We have a Kálmán filter prediction based on a prior state. And then we have a distribution, the prior distribution. So we have a prediction that we seed it with. This is what we think it is. It's a guess originally. Then we have the prior distribution based on history. That comes in. And then we take the data and we get an update. Then that creates a new posterior distribution, which goes back into the Kálmán filter prediction process. So the Kálmán filter is used to make noisy data less noisy, and it can be used either for filtering data or estimation. It provides process information in a probability space as it takes data and converts it into a Bayesian estimate. This is the probability of the future state given what we know about it today. The probabilities of the past, the prior distributions, plus the noise and the measurement value of the current state. So the Kálmán filter is said to lock onto a solution when it converges as a probability vector that provides an accurate estimate of the noise effect on the data flow. Now, there's a wide variety of Kálmán algorithms, and to gain a deep understanding, it's best to start with a basic tutorial and expand from there. So again, at the base here of this slide, there's a tutorial. So if you want to learn about Kálmán filtering, how they operate, you're going to have to invest a few hours of your time, and this is a good place to start. So we need to understand Markov processes in Bayesian state space. This is exactly what we're thinking about. Now, every time we have new technologies come along, those technologies are constantly introducing new vocabularies. And they will then create confusion and upset meanings that are embedded in our old ways of thinking. So I'm going to now define some of the terms that are coming out in this state so we can try to understand them and how they apply. So a stochastic process is basically a process where we have a sequence of events in which the outcome at any stage depends on probabilities. And we analyze then the probability distribution, and we only are making predictions probabilistically. So each variable changes randomly, but under some conditions in the shared probability space. So we can take many different factors in there. So for example, if we take a look at a chemical process, we may say temperature, pressure, flow rate, and initial state of raw material are all factors. And if we analyze each of those one factor at a time, like using an SPC chart, then a suboptimal estimate of the total result is obtained. So if we combine all of them together, then we can get a more accurate prediction of the process. Now, a Markov process is where we have a series of these process steps. Each one of them is being analyzed for its stochastic processes. So what's happening inside that process, and then what is the sequence of those probabilities as we chain them or link them together. So the probability success across here steps A through F is equal to the product of the success probabilities of all 6 steps. For any black belts out there, you will know this as the same concept as rolled throughput yield. Now, state conditions, any system, a series of Markov states, if you will, can be represented as a state space. And a state or condition of a system can be represented as a vector in that space. The space is the process boundaries. So state space metrics, or an SSM, collects and combines data and expresses them as a vector from the starting position and a director of motion. So state vectors can be either an absolute measurement or a probability vector. So the absolute measurement shows the actual number of objects and then how they're measured. The probability vector says this is actually the probabilities. Now, in the state of maximum control, we are only using probability vectors. So this is another change. We have to start learning to think with probability. Each vector then is represented in a probability decision tree where observed states are noticed. That's situational awareness with a degree of probabilistic noise around that. And that gives us these environmental and measured signals based on contributions from those measurement and detection devices that we have put in the system as sensors. A recursive process is one that uses feedback loops and they work together recursively. So any process which has a base case and is repeated and we apply the same analysis to get more simple versions of it is recursive. So the value of the outcome at an early time may influence the value at a later time. And though each of the steps in the process is going to have its unique set of rules and the way it influences the system, these recursive processes will give us some estimate of not only the base case, but where is it going over time as we start seeing that same analytic method applied, and it gets better and better. Now, recursive algorithms can be used across a Markov process. And these Markov decision processes are basically the fundamental structure for modeling all control problems as a sequence of stochastic environments. The Bayesian process is something that maybe you're familiar with already, but we think of basically probability theory as what I call statistical storytelling. So any process operating according to conditional probability where its outcome is given by the prior state. So we have the probability of an outcome, B, given A, the prior state. That's a Bayesian expectation. So Kálmán filtering allows all of these factors to be analyzed by processing their unique measurement conditions, converting them to a multi-dimensional probability space as a probability density function, and then to assess the conjoint outcome of the multiple vector signals in achieving a minimal covariance vector. So the logic that we're dealing with this, and logic I look at as the engineering function of philosophy because it's allowing choices to be made on input data and developing consistent outputs. So the decision logic that we're going to be applying here is the operation of process or a series of processes or policy rules, policy decisions, that are based on the observed conditions we have and what prior information we had, the seed, which could come from history, or it's a guess, if you will, to the cumulative distribution as we take all of this information together and we apply this Bayesian conditional logic to that state space matrix. So choices branch from the original condition out to a variety of things. And so we can start understanding this because what we see in this state space matrix is a transition probabilities between these observed states in each of those Markov states. And so that's going to be represented as a covariance matrix between all of those different factors to see how are they affecting the outcome at each stage in the process. So the final definition is matrix mathematics. And here we've given you already a tutorial on eigenvectors, another one on Kálmán filtering, but here is one on a more basic explanation of the Kálmán filter and a tutorial on matrix mathematics or matrix algebra. And we see here are the various variables that are used in a Kálmán filter. So we see that there's state variables, those are measures. There are also measurements about them. So the state variable is the factor, and then the z is the measurement of the factor. And so we can have also a number of matrices. So we have a P matrix, an A matrix, an H matrix, an R matrix, if you will, which is a covariance matrix. And then we have a noise covariance matrix, and then a Kálmán gain. And so as we start taking a look, these are the manipulations that are going to be happening in the matrix math of the Kálmán filter. So how do we operate a Kálmán filter? How does it actually working? So we're going to keep this at a high level again. But basically what we're doing is we have some sort of difference. This is the difference between the prior estimate and the current estimate. So that's delta 0 as initial state. That goes into a workstation. We then operate the workstation and we have control coming out. And then we see delta 1. That's a difference between workstation 1 and workstation 2 from the past iteration. Then we operate workstation 2 and we've got now delta 2. So delta 2 is a difference between workstation 2 and its prior and its current. And then we have delta 0 coming out of workstation n at the end. And we see non-conforming coming out, some going to strap, some going to rework. So what we have is that we have a series of Markov states. Each of those states is Bayesian, and the cumulative probability effects is based on prior results at each step in the process. These states are dynamic because within each of those states, they can change based on the observed measurements and the uncertainty we see in signal flow, as well as noise conditions. And the results are stochastic. They're measured as a cumulative probability distribution function, both within each of the workstations or subprocesses and across the combination of those processes. So when we're processing noisy data, to get less noisy data, we see that the sources of noise in the Kálmán filter are threefold. One is measurement error uncertainty, and then it's from measurement in the error components, and it's also from uncertainty in that original estimate. Did we make a guess? Do we have a bad history? Did we change something? So what are those probability distributions? And here we see that we have these measurements, and we see we have some measurement uncertainty if there. We have this accuracy of the measurement between where it is and the true value. We have the expected value of this given some sort of assumed probability density function. And so here we're assuming a normal, may not be normal. So what is that probability density function? How can we determine it? So when we operate this Kálmán state space vector, what we start seeing is that these individual system states have some sort of individual uncertainty. So we see we have inputs, and so one input is the measure. It goes into the Kálmán filter. We update the process, and out of that is an output, which is the state estimate or future uncertainty. We have another input coming in, which was the initial state. What was the guess? What did we seed it with as a prior probability distribution? And from this, we get a result. And then we have an output, which is a delay between the two observations in the system. So how big is that process and how much of a delay is happening? So if we take a look in this, we can see that we have a static measurement step. So step 1 is we take a measure. Step 2 is we calculate the Kálmán gain from the posterior distribution. Step 3 is we have this output, and it's being then done, manipulated by the initialization vector that comes from that first guess. It then predicts the future state, and then that's the feedback loop for the recursive estimations. So this represents a single step in a sequence of Markov states. So every Markov state in the sequence of the chain of events in a process would be doing exactly this type of filtering system. And we take a look at this operation, what we see is we have this performance data where the past knowledge, so in the bottom left-hand side, you'll see the prior distribution of the state. It's kind of fuzzy, and it's got an orientation of that ellipse, and it's changing, so we get a new outcome at the end of this. So this is when I said we're working in probability space. This is exactly what I mean. This is the probability space where we're operating. So let me talk about this example of applying a Kálmán algorithm. So we can apply these for SPC, where we have autocorrelation using state space models. We can do it for model-based multi-scale filtering, for instance, using Kálmán filtering in combination with some physics like wavelet theory. We can do sensor fusion from multiple sources with different acquisition rates, different qualities, uncertainty levels, different data structures, images, sensors, different spectra. So the real power of the Kálmán filter is not in smoothing the data, it's in its ability to estimate system parameters that we cannot directly measure. So I measure individual things, but what's the probability of success of all of it? Well, we don't measure that directly, but we can derive it from the Kálmán filtering process. So what does it look like if we're going to be doing Kálmán filtering or Kálmán estimation? So here is an example of the output of a Kálmán filter. And if we take a look at this, we start seeing that this Y is this very noisy, spiky thing, and we're taking a look at the position, and we see that the true signal is one where there's no noise, and then the Kálmán estimate is basically right on top of it. And so when we're talking about as a data filter, we can actually get very close understandings. But another value for that, that's important for tracking something. But there's another value is a state estimator. So here we see the individual measurement estimator, and we see it's very good. But what it can also do is give us and help us recover with good accuracy four-dimensional state vectors that fully characterize the system. Those are those individual states at the bottom. So those are not part of the measurement, but they may be contributing to the measure in an indirect way. And so we can actually then derive those out of the Kálmán filter by how we do this estimation process. How we do it? You have to go through the tutorials to understand it. That's what I'm saying, that it's going to take some study. It's going to take some time for you to really get to this. But what we want to do is show that there is value in this maximum probability estimation, and that maximum control is a real thing for us to think about in the quality community. So what is the future of Quality 4.0, SPC, engineering process control monitoring, and also simulation with digital twins, which now opens a whole new probability function for us to think about. So the emerging situation will be engaging the artificial and the real. This is what digital twinning does. So we're modeling operational performance, and that enables simulation of variables as an input using these probability maps from Kálmán filtering, maybe even combined with artificial intelligence, machine learning algorithm outputs, and to get a much more complete and fuller understanding of situations. So as we look at this, we see we have real-world data streams. So there's a real-world data coming in. We have a digital twin. That's the abstract model of this man-machine system. And we can compare the two to understand what is the estimation of this. So this poses a practical question. When we take a look at this, where do we need corrections? Do we need to fix a real-world system, or is it a simulated system? So have we validated that simulated system so we have high confidence in what it does, or do we need to correct the real-world situation to get it so that it locks onto what needs to be done? Using a Kálmán filter approach, we can actually distinguish between those objectives. So what are the implications of this process? Well, first, today many organizations are considering investing in digitization, robotics, and automation, and particular interest in solutions that deliver low-cost automation. Because we don't want to make mistakes in investing, because it can be a lot of money, it can be a lot of infrastructure changes as we move forward. Shewhart's maximum control has become a possibility as preconditions of QA for digital processes are met with development of digital sensors, ability to monitor quality characteristics that are appropriate for process control. Systems engineering enables proper positioning of these sensors, and the use of high sampling rates assures a continuous flow of data, collecting observations and data historians, which allows implementation of real-time feedback loops for automated control systems that can then be used to adjust variables and control the state space of the key quality characteristics, the output characteristics, and yield what we would say at the end, quality control. So engineering process control thus realizes maximum control, which occurs when the EPC system gains QC of the product through an adaptive dynamic process of quality assurance for the end-to-end process. Well, that's the end of the prepared presentation today. We have time for some Q&A, so I'm going to turn over and just ask, have we had some questions about this presentation? And I want to remind you, embedded in the PDF that you'll see are these 3 or 4 different types of tutorials that you'll find helpful for future study on this subject as you learn about it and how to make it useful in potentially your future. Thank you.